Hello, and welcome to our short course on models of social dynamics. I'm Paul Smaldino. I'm an assistant professor of cognitive and information sciences at the University of California, Merced. And in this unit, we'll tackle the dynamics of opinions and polarization. So, the thing about the contagion model we studied in the last unit is contagion is binary. You're either infected or you're not. You either adopt a product or a behavior or a belief, or you don't. And this is a good model for some situations, but not for others. In particular, if we're interested in how social information spreads, we often have to get a bit more nuanced. So here we're going to talk about opinions, beliefs, and attitudes. And these are all somewhat different from one another in the way they're usually used. But for the sake of tractability here, I'll treat them equivalently and stick in general with the term opinion. An opinion, as we're going to model it, is a position on some issue. Right? So, do you like cake? Is Batman really a hero? Is the theory of natural selection true? In addition to being ruthlessly for or against a particular opinion, so yes or no, individuals can also be ambivalent or lean weakly for or against. So in this case, opinions for things can vary along a continuum. And moreover, the opinion itself doesn't have to be a binary yes or no question. It can be quantitative. So how much should one pray? How many licks does it take to get to the Tootsie Roll center of a Tootsie Pop? So in this unit, we'll use models to explore how our assumptions about social influence affects the long-run distribution of opinions in a population. Okay. A model of social influence requires assumptions of three categories at least. First, we need a representation of those opinions, attitudes, or beliefs. Right? So, what do we mean when we say an individual has a certain opinion or certain opinions? Two, we need a mechanism for social influence. So, how do agents' opinions change over time through interactions with others? And three, we need a population structure, so who interacts with who and when. So let's look at these in more detail. So first, a representation of opinion. Ultimately, opinions might be complex enough to warrant a sophisticated cognitive model of the representation, such as, let's say, a multidimensional semantic network. Right? Opinions are cognitive phenomena, and this is a worthy goal, but for the sake of starting simple, we're going to assume that an individual can hold an opinion on any number of topics and will represent all their opinions as a vector in which each item is one opinion. The values of an opinion, can take might be either discrete or continuous. And in this unit, we're going to focus on continuous. So let's consider an opinion that can vary between 0 and 1. If we consider only one opinion with only two possible values, we arrive back at our contagion model from the previous unit, in which opinions are represented as either held or not held. Right? So therefore, in a sense, the contagion model is a special case of the opinion model. Let's see. In the interest of sticking with simple models and adding only a little bit of complexity at a time, we're going to continue in this unit by sticking with agents that hold only one opinion, but now that opinion can take on any continuous value between two extremes. So we'll here represent an opinion on whatever issue as a real number between 0 and 1, with those numbers representing the most oppositional and extreme opinions an individual can hold, and values in between representing moderate or ambivalent opinions. Okay, next we need a mechanism for social influence. Right? How do opinions change as a result of social interaction? If two agents interact, how do they influence each other? How do opinions change as a result of that influence? So in our contagion model, each simply had a fixed probability of infecting another agent with its belief, but that won't work in the case of continuous valued opinions. We need to quantify exactly how opinions are influenced. A number of our assumptions can draw from the psychological literature, which has produced a fairly large amount of research on social influence, and we can formalize some of those ideas here. I'll focus on three. First, positive influence. Right? Agents interact, and through that interaction, they become more similar. Next, bounded confidence, also sometimes called biased assimilation. And in this case, agents ignore those that are sufficiently different. So the idea is that individuals are readily influenced by those with whom they're already in substantial agreement, but they're more skeptical of opinions shared by individuals with whom they differ. So we can represent this as a threshold for influence. So if individuals are sufficiently different in opinion, they don't influence one another at all. And a sort of more extreme case of that is negative influence. This is an alternative view, honestly, for which there's mixed empirical support, but it's often worthwhile examining assumptions for which there's mixed empirical support, is one in which individuals who differ actually grow more dissimilar. So in other words, interactions with those whose opinions differ substantially from your own might push you toward a more extreme version of initial views. And we'll explore versions of the model with both bounded confidence and negative influence, and we'll always have positive influence. Okay, lastly, population structure. Who interacts with whom? So in the previous unit, we saw that the rate of population mixing could influence the spread of a contagion in the SIS model case. So here we're just going to focus on two extremes. At one extreme, we'll consider a random mixing model, where individuals pair totally at random, and there's basically no structure. On the other extreme, we can consider a population with a rigid, unchanging network structure in which each individual only interacts with their 4 other network neighbors. And this is going to give us, allow us to have some intuition about how population structure influences opinion dynamics by comparing these two extremes. All right, let's get to the model. We're going to be looking at something called the bounded confidence model, which is based on a 2000 paper by Defwan et al. And we'll make a population of agents, each characterized by, to begin with, just one opinion. And for simplicity, we'll initialize those opinions as randomly drawn in the range of 0 to 1. So initially, there's just a uniform distribution of opinions. Each tick of the simulation clock, 2 agents will interact, and if they are sufficiently similar, they will become more similar through positive influence. So how does this work? So let's assume 2 opinions, x1 and x2, and a confidence threshold d and a learning rate k. So if the absolute difference between x1 and x2 is greater than or equal to d, so it's beyond the confidence threshold, the 2 agents just totally ignore each other and nothing happens. Otherwise, if they're close enough, the opinion of agent 1 is updated like this in the first equation here. It becomes, it sort of moves toward the opinion of agent 2, a fraction k. So k is the fraction proportion of the distance moved toward agent 2. And agent 2's opinion will update similarly toward that of agent 1. Okay, how does an agent, I said that agents, 2 agents pair up. How do they do that, right? So if we're just thinking about the random mixing case, then an agent chooses a partner at random, just a random from the population. Otherwise, it chooses it on a square lattice. It chooses one of its network neighbors. So we can put agents on a square lattice. Each agent occupies a cell on the grid. So this will be one patch in NetLogo. And then we just restrict interaction partners to one of the closest 4 neighbors, so up, down, left, right on the grid. So it's this one, this left one here. This is sometimes called the von Neumann neighborhood, after the mathematician and computer science pioneer John von Neumann. Another common way to represent neighbors in a square lattice is to use the nearest 8 neighbors. This is sometimes called the Moore neighborhood, also after a mathematician who studied this kind of system. But to keep this thing simple, we're going to use the von Neumann neighborhood, so nearest 4 neighbors, for this model and for all subsequent spatial models throughout this course. Basically, the entire gambit of social network analysis is that interactions are not random, but occur based on social ties. The square lattice is not the most realistic network structure, but it is among the easiest to model computationally, and it does give us some intuition for how structure influences social dynamics, which is one of the reasons we're going to use it. Okay, so now that we've got our model figured out, like I said, it's very simple. All agents hold one opinion, and then agents pair up and either influence each other if they're close enough or don't. And let's think about what would happen. We can build this into a simulation. So open up the bounded confidence model. This is opinion dynamics _BC, that N logo. So for this model, we'll also explore several options for plotting information about models dynamics. So here is our code, and you see we have, here is our net logo model. We've got a slider for the learning rate, K. And I'm just going to leave that fixed at 0.3. It doesn't have a huge effect on the ultimate results. And then here's the confidence threshold, D. And then here's our switch for whether or not we're going to use spatial structure. So when this is off, agents pair up at random, and when it's on, agents choose one of their spatial neighbors for interaction. Let's look at the code for a second. It's very simple. Each agent has its own opinion, which it keeps track of. When the model is initialized, I'm going to do something here that just allows agents to exist one per patch. So instead of asking turtles or creating turtles, I'm going to ask all the patches to sprout one, which means basically create a turtle on the patch. So on whatever patch is being asked, sprout one, and then set its opinion to a random number between 0 and 1, and it's shaped a circle. And then we update colors. So I have a procedure down here called update colors, which just sets the color of the turtle a function of its opinion. What this does is it means that opinions that are equal to 0 will be black, opinions that are equal to 1 will be white, and shades of gray in between. That's it for setup. The dynamics of the model work like this. Ask one of turtles, so we choose one turtle at random, and x1 is going to be its opinion. And then select another turtle, which will be one of other turtles, so just one of the other turtles that are not the turtle in question. But if we're using spatial interactions, we're going to set the other turtle to one of other turtles on neighbors 4. This means actually switch it to one of my 4 closest neighbors. And x2 will be the opinion of that other turtle. And here we'll just check, is the absolute difference between their 2 opinions below the confidence threshold? If it is, each one is updated and grows toward the other one with a proportion which is determined by the learning rate. And then they set their new opinions and then update their colors. And that's it. That's all we do. Okay, so I said we're going to use a few different visualization techniques. So if I set up this model, you can see here, all right, all the agents are in this population and they've got different colored opinions. Also, though, we can represent the agent opinions as a histogram. And so here's our nice histogram, which is, again, very easy to set up in NetLogo. And this will change as the agent's opinions change. What's nice about the histogram is it really gives us a really good sense of where the opinions are numerically. But what it doesn't show us well is the dynamics over time of those opinions. So what I've done here is create a scatter plot where the x-axis is time and the y-axis is every agent's opinion. And so this will change over time. And I'm not going to, this runs a little slow with my video running. So instead I'm just going to show you screenshots of what this looks like as we examine the different results. So if the confidence threshold is large, like 0.5, what we get is consensus. Every agent ends up being influenced toward the middle, and then basically all the agents are right around 0.5. And this is true even though individuals initially exclude extremely different opinions, right? The agents down near the bottom, with opinions close to 0, they're ignoring the ones up here. But the agents in this realm are becoming closer to each other. Agents here are becoming closer. And what you get is that even though the ones with opinions close to 0 are initially ignoring the ones close to 1 and vice versa, through random mixing, all of the population becomes more similar. When we make the threshold a little smaller, so here it's 0.35, we still get consensus. But we start seeing what Def1 et al. Call wings, so a few individuals that have extreme values persist in the population. So here there's just 2 with these opinions close to 0, and they're persisting. You can see them on the graph, or on the patches with their different opinions. Notably, you get consensus even with a confidence threshold that's a lot smaller than the full range. Most people are ignoring 2/3 of the other people, but you still get consensus with this distribution. And you can get global consensus even with d equals 0.3. As we lower d gets smaller, all of a sudden we see the emergence of cliques. The smaller d is the more cliques we get. So here, where everyone is ignoring those with opinions that are substantially different from theirs, here the confidence interval is 0.12. So everyone is ignoring anyone whose opinion is more than 0.12 amount different from them. What you get is these little communities that form where everyone has the same opinion within the clique, but there are several different cliques with different opinions on this issue. And here we can just look at some data from Def1 et al.'s analysis. On the left graph, we can see a clear demonstration that smaller d means more cliques. So when d is large, right, we get 1 peak, everyone goes to the same value. As d goes down, we start getting 2 peaks, 3, 4, 5, 6. We also see that agents' initial positions, where they end up, are correlated with their final position, or with their initial position, sorry. Agents' final positions are correlated with their initial positions, but there's some uncertainty due to stochasticity and who interacts with whom in what order. So this right figure here is from one simulation where there end up being 4 cliques, so d is 0.1 here. And you can see that among those that started with an opinion around 0.2, some ended up in the clique that was around a little bit less than 0.1, and some ended up in the clique that was closer to 0.4. So it really just was a matter of random chance of who tended to interact with whom in what order and how opinions shifted. Okay, that's what happens when individuals interact at random. What happens when individuals interact with only their network neighbors? Things look a little different. So here we're considering, again, a confidence interval of 0.35, where before we had very strong consensus in the middle with just a couple of little wings, but it looks like now is quite different. So even though the square lattice is a very simple sort of social network, comparing it to the well-mixed version, the non-spatial version, can give us an intuition about how the model responds to variations in population structure. So even though we get consensus, the main difference is that there is an increased likelihood in extremists persisting. So here we see quite a few extreme opinions persisting. And, right, so here they're kind of isolated, so they're different enough from their neighbors that they're not changing, and they're not close enough to anyone who has a similar opinion enough that it's going to change them. So you get this persistence of these extreme opinions. Also, the distribution of opinions around the middle remains wide for very long, because opinions take longer to percolate through the network, and the model only allows, because the way the model works, it allows small differences to persist for a long time, because opinion change is a fixed proportion of the difference in two agents' opinions. So if you're very similar to your neighbor, even if they're a little different, you're going to change very, very little because you're only moving a fraction of the distance between you two. All right, as D gets smaller, as the confidence interval becomes less, the dynamics start to look even more different from the non-spatial version. So instead of a few clusters that are all kind of at the same size, that are all very clearly delineated, like we saw in the non-spatial model, here we often get one big cluster that percolates through the network and gets a lot of traction. So here's a confidence interval is 0.25. You get one big cluster. You can kind of see it here where all the agents are kind of similar in the middle, and this is the giant gray blob that's spread throughout. But you also get a bunch of little spots of other opinions that persist. That doesn't always happen. This is another run with the exact same parameters, but you get a lot more persistent variation. So people and their agents in the model now have only a few individuals in their neighborhood who are sufficiently similar to them, and opinions can't easily spread beyond local networks. So the take home here is if we assume strong network structure, we get seemingly contradictory consequences. One, we get a lot of broad consensus in the population among the majority, but we also get the persistence of small factions with extreme or idiosyncratic opinions. So both of the models, the non-spatial and the spatial versions, show how group differences can persist, even if all influence is positive, as long as differences lead to a lack of influence. Right? What if we consider instead the case where differences lead to action, so the exacerbation of differences? So let's look at negative influence. Right? And so far we've assumed that individuals simply ignore others with whom they differ sufficiently, but here we'll consider the case where those differences are exacerbated. Instead of ignoring the opinions that are more than D different from one's own, agents now update their opinions to be increasingly different. So let's see what happens. Do we still see this emergence of cliques? So positive influence in this model works exactly the same. If the difference in agents' opinions are within the confidence threshold D, the model works as before. Positive social influence, they move their opinions toward one another by proportion K. However, if their opinions are sufficiently different, instead of ignoring each other, they now exert negative influence, moving toward the extremes by a proportion K of that distance. So we can look at the bounded confidence model now with negative influence. And again, I'm just going to briefly show you the code, but all the results I'll use screenshots. So now we've just added one more switch called repulsion. When repulsion is off, we have our standard bounded confidence model just like before. With repulsion on, we have negative influence. And the only thing I've done to change things is say if, so here we have, if the difference in opinions is below the confidence threshold, they have a positive influence. But otherwise, if it's greater than the confidence threshold and we're using repulsion, then they move away from each other. And I have two different if statements depending on which order is, if A is greater, or x1 is greater than x2, or vice versa, just to make the math easier. So let's see what happens. Okay, if the confidence threshold is large, so greater than 0.5, the model still leads to consensus pretty much every time. It's just going to end up back at 0.5. When the threshold is close to 0.5, though, sometimes even we get something interesting happen. We do get consensus, so all the agents kind of converge toward the middle, but sometimes a couple agents, 1, 2, 3 agents, will end up being pushed away and going toward extreme values. And if, because those extreme values all the way at 1 or all the way at 0 might be just enough far away, so let's say like 0.51 different from that consensus, there's gonna be repulsion. Now, if you're at an extreme, you can't move any farther, but it does push everyone else. So it pushes the rest of the population in the opposite direction. So gradually, over time, the existence of extremists occasionally interacting with the rest of the population pushes the entire rest of the population slowly but surely toward the opposite extreme. If D gets a little bit lower, like here's 0.4, the population just goes right toward polarization to the extreme. So roughly equal numbers in both camps. So instead of consensus toward the middle, we just get a split, and everyone just goes to either 0 or 1. If you keep lowering D so that people are repelled from most others, so most other individuals you're trying to move away from, something interesting happens. You again get attraction to the extremes, but in this case, there is the perseverance of many intermediate opinions, right? Because those with moderate opinions are constantly pushed both up and down, up and down, up and down, depending on who they interact with. And this is particularly the case if you have a small learning rate, so that most opinion changes are small, so you get, again, the perseverance of those moderate opinions. All right, that's the non-spatial model where interactions are at random. What about the spatial model? So in the spatial model, again, if D is greater than 0.5, we get clustering around the mean consensus. But we still get some persistent variation due to sort of the fact that opinions have to percolate in space throughout the network. And any agents near extremists will be continuously pushed in multiple directions. They'll be pushed away from the extreme by the extremists and toward the other side by their neighbors. So here is confidence threshold of 0.5, and we see this emergence of polarized zones beginning. Right? It takes a while, and there's a lot of persistence of variation. The dynamics can take quite a long time to unfurl, but look at this. You have a lot of variation. Almost all opinions are represented for a very long time. Most agents are kind of in the middle. You can see this very clearly here. There's a peak kind of in the intermediate, but opinions across the spectrum are represented. And you can kind of see here a boundary is starting to emerge where these opinions very close to 1 are pushed up against these opinions close to 0.5, and these ones in the middle don't quite know where to go. Right. As the confidence threshold goes down, you start getting clearer boundaries, right? So here's at D is 0.5, right? Once we get to D 0.35, look at this. We get very clear zones of opinion 1 and zones of opinion 0. When D is very low, like 0.1, and most individuals are pushed away from many others, you get this very interesting effect where you get these small smatterings of both extremes, but there's no continuity between them because everyone is repelled by everyone initially. And so you get neighbors being pushed away from each other, and a lot of sort of, it looks almost like a uniform distribution throughout the space of each opinion. So everyone still holds extreme opinions in the same proportions as with D is 0.35, but there's no longer blocks of unified opinions. All right. So what does this all mean? What are these models that we've been playing with this unit? Among the approaches to modeling social influence and interaction that we're going to consider in this course, opinion dynamics are among the youngest. fits to empirical data and deep considerations of the cognitive aspects of opinion representation and social influence in the models are still relatively rare, and what work on that there is very new. Right? Much of what's been done here is simply to start by making some arbitrary assumptions and examining the consequences, many of which aren't particularly intuitive. I also include these models because I think that they yield interesting dynamics and provide a good baseline upon which to construct richer models. I also think that there's a lot of open territory for the industrious scientist who wants to combine the cognitive science and sociology of opinions. How opinions spread is a very challenging system to model well because of the inherent difficulties in modeling both complex social interactions and complex cognitive phenomena. To do this right, we need to know a lot more about the sociology of communicative interactions and the cognitive science of influence as it interacts with things like language, bias, and identity, among others. For what it's worth, the increasing communication between social scientists, cultural evolutionists, and cognitive scientists is, I think, encouraging. So let's talk some further directions. Differentiation. So individuals might not just become more similar to others, or when they're already similar. They might actually actively seek to differentiate others from others to whom they're currently similar. Such models have shown that preferences for differentiation can, under a wide range of conditions, nevertheless lead to conformity at the population level, which I think is pretty interesting. However, if both anticonformists and conformists coexist, there's some research suggesting that anticonformists might drive the persistence of extreme opinions and therefore drive polarization even in the absence of negative influence. Another direction broadly is the idea of multiple interacting opinions. In the model we just looked at agents with a single opinion, and they only looked at other agents on one opinion. But actually, people have more than one opinion, and this might influence perceptions of similarity and differences. As similarity on sufficient opinions might facilitate positive influence on an opinion on which individuals differ greatly. So we might have a very different opinion on something, but if we're generally similar, I might be willing to listen to what you have to say on this topic that we initially differ a lot. So there are a bunch of papers, some of which are now kind of classics in the study of opinions and the emergence of communities, work by people like Robert Axelrod and Noah Mark, among others. Network structure. So in our model, we considered very simple network structure, a square lattice. But real social networks are often more tightly clustered. There's more varied betweenness among agents. There's just more interesting structures. So one example, Flocka and Macy in 2011 considered vectors of opinions and negative influence on a structure called a connected caveman graph. And they looked at how the introduction of long-range ties between communities might influence the prevalence of extreme positions and polarization. This might provide a possible explanation for, let's say, how the internet and social media could lead to greater social polarization. And finally, there's some related work on beliefs. So I said, I wasn't going to differentiate between opinions and beliefs in the unit, but the difference, right, is that beliefs, to some extent, might be true or useful or not. Right? Some beliefs might be more useful or true than others. But it's also clear that misinformation spreads. So there are some interesting models of social influence that have used factors like network structure and conformity to examine questions about the spread of misinformation or let's say, methods that lead less often to true beliefs, often in the context of scientific communities. Okay, that concludes our unit on opinions. Next up, cooperation. Thanks for watching.